All right, welcome. We're going to start our part three of our notes. I can't believe we're already up to lecture number three, and today, in fact, I'm just going to call this, we'll start it off with, we'll call it electricity number three, because that's where we are. We're talking about electricity still, and this is now lecture number three. So we've talked so far about what is electricity. We talked about drawing circuit diagrams and the different symbols for it, and what makes a circuit, and what makes an open circuit and a closed circuit, and what makes a short circuit. So today we're going to talk about some of the more measurable things in electricity, the things that we actually look at when we're analyzing a circuit to determine usage and safety and all these other little factors that go into that. And the first thing, and we've introduced the term before, but we'll introduce it again, that we're going to talk about is we're going to talk about current to start off. So we have already said electric current is moving electrons. We said that back in that first lecture. So that's what current is. We measure current in a unit called amperes. Or sometimes they're just shortened to amps. And the symbol for an ampere is A. So, for example, I could have 2 amps of current. And ampere is kind of like when we're talking about that water analogy, it could be like the gallons of water that are moving through the hose. So it's the actual amount of electrons moving through. So it's the rate. I'm sorry, it's not really it's the rate at which those gallons move through, I mean. So it's like gallons of water per, when we put something over top of something, that's a way of saying per, second. So again, it's like that with our water analogy, but it's really, it's charge, the amount of electric charge per second. So that is what an ampere is. So current, when we look at how current moves about in a circuit, current flows through a circuit just like water flows through pipes. And we talked about how to get current to flow, or rather, I'm sorry, we're going to talk about how to get current to flow, we have to move from areas where there's lots of energy to areas where there's less energy. So current flows from, and this is how we draw it. We draw current flowing from the plus sides, the positive sides, from the positive to the negative. Even though we're talking about electrons, and we're talking about how electrons move around in a circuit, and electrons are the ones that actually do everything, for some reason, a long time ago, they decided they were going to draw how positive things would move through a circuit instead of how the negative things move through the circuit. And I've never really gotten a clear answer as to why that is, but I think it has to do with the fact that they didn't know that was the which it was, whether it was the positive stuff or the negative stuff that moved through electricity in the beginning. But so even though really in a wire it's the electrons moving, when we talk about current flow and we talk about how it's moving through a circuit, we always talk about it from the perspective as if it was positive. So we kind of actually look at it in a little bit of a backwards way. But not really super crucial, but just so you know, when we draw how current moves, we draw it from positive to the negative. So this is an important fact about current, and it will lead us to a lot of rules, and it's pretty simple to get, and that is whatever you put in to something, as far as you put electrons into a light bulb, the current in must equal the current out. So if I put 1 amp into a light bulb, on the other side of that light bulb, 1 amp needs to be coming out. It's a simple fact that I can't make electrons and I can't destroy electrons, which means whatever I put in, I got to get out. So if anything, think of electrons in a wire like maybe a tube full of marbles. And when you push one new marble in, the other one pops out the other side. And so every time you push a new marble in at one end of the wire, one marble pops out the other side. So the electrons are like the marbles, and that tube is the wire. So as you shove in electrons on one side, electrons immediately pop out the other side. Not the same electron, but another electron further down the wire pops out the other side. All right, so moving on, that's current. Current's that flow of electricity. For current to happen, you must first have something called a voltage. And voltage is a way to measure electric potential energy. But it's not electric potential energy. It's related. They're connected. It's different. So specifically, voltage is energy and per, right? We put something over top of something, that means per charge. That's what voltage really is. Or excuse me, that's what volts really is. Voltage, so that's a volt. Voltage is different because voltage is the difference in the energy per charge between two spots circuit. It's a little bit weird when you say it, but if you can follow this analogy that I'm going to give you, it's going to help a lot. So think of it like this. If I have cliff, it's a flat cliff way up high above the ground. Okay? And I've got a ball. And that ball's just sitting there right now. I take the ball, I set it down on the ground. If I let go of that ball right there, it's not going to move. The ground's flat. There's no difference in height. So, since there's no difference in height, there's also no difference in energy. It does have potential energy because it's above the ground, right? It has some height. But between where the ball is And anywhere along here until you get to the edge of the cliff, or this way for however long the ground goes, there's no real difference in height. And yeah, the line's a little wavy and whatever, but that's just my drawing skills, so there you go. So there's no difference in the height there. So to get the current to flow, or to get the ball to roll, I need a difference in height. I need to have this ball someplace where there's a height here and there's a height here. So now the ball will roll down the hill. There is a difference. So if there is a difference, which is a voltage, if there's a difference in that energy from one spot in a circuit to another, then current will flow. For example, if I look at a battery, like those D cells that we used in class, I have a battery sitting here. If I take and measure from here over on this side, there's 1 volt, or sorry, 1.5 volts, excuse me. 1.5 volts. Over here, there's 1 volt. Excuse me, no, that's wrong. There's 0 volts. What am I thinking here? On this side, there's 0 volts. So the difference, the change, right? Remember, triangles mean deltas. Those mean change in voltage, or volts. That's the voltage, is 1 volt. So electricity will move from one end around to the other if I connect it with a wire. If I give it a path, it'll do that. All right, this is pretty close to where I want to stop. I want to slip one last thing in here real quick. I'm going to write down the term, and we're going to talk about it in class a lot. But a multimeter, this is a device used for measuring current, voltage, and resistance. We're going to use these a lot in class over the next few days, weeks, and probably month. All right, we'll stop there. It's about 13 minutes, so a little bit longer this time. Hope you learned something. If you have any questions, come into class, and I'll see you then.